So in this video, we're going to continue on with our discussion of perturbations to the hydrogen atom and specifically this Zeeman effect. So last video we discussed the Zeeman effect, which is essentially if we apply an external magnetic field to an atom, we can see a shift in some of the energy levels. And we looked at the low field limit um, in the last case, and what we had was that the Hamiltonian of our system was just our unperturbed hydrogen atom plus the fine structure term and this now Zeeman term that we were discussing. And what we did was, well, depending on the strength of the magnetic field we applied, the Zeeman term um, can be large or small. It's proportional to the magnetic field. So what we do in the low field limit is we essentially look at what we had for the hydrogen atom, including the perturbations to the fine structure terms and that. And we use that as our zeroth order states and energies, and then we applied the Zeeman term as our perturbation uh, to that system. And what this all resulted in was that the corrections due to that Zeeman term to first order were essentially just mu b times the magnetic field strength times the mj 1 plus or minus 1 over 2L plus 1. And so we had determined how our energy levels changed, the corrections to those states in when the magnetic field was small, when we were in that low field limit. Today, in this video, we're going to look at the high field case, where the opposite is going to be true, where this Zeeman term, because of the large magnetic field, is going to be stronger. And our approach is essentially going to be to apply it first, that perturbation first, so that our zeroth order states are determined by our unperturbed hydrogen states after they've been perturbed by that Zeeman term. So we'll take that as our zeroth order states, and then apply the fine structure term as our perturbation. So the first thing we have to do is determine what our zeroth order states are, right? So if we recall that Zeeman Hamiltonian is, excuse me, equal to mu b times the magnetic field strength over h bar times the orbital gyroscopic ratio times the z component of the orbital angular momentum plus the electron g factor times the z component of the spin angular momentum. And this is diagonal in the uncoupled bases. Since it's the first perturbation we're applying, we're just going to use that uncoupled bases to get the energy shifts due to that this perturbation. So we end up, calculating those first order energy shifts or the first order energy corrections in that NLS M sub L M sub S bases that this is diagonal in, and that is really quick to calculate because we know that that we chose this basis because it's diagonal in that. The action of that Hamiltonian on these basis states gives us an eigenvalue equation, but we essentially can really quickly see that that energy shift is equal to GL times M sub L plus GE times M sub S. Or if we use the hydrogen atom, that GL is 1, the GE is 2. So this gives us mu sub B, B over H bar, the orbital magnetic quantum number plus 2 times the spin magnetic quantum number. And that is our first order shift due to our strong Zeeman external magnetic field. And the perturbed eigenstates are actually just these same NLS, ML, NS states. It's a first order, it's diagonal in that basis. The next thing we have to do is Now that we have our what we're going to call our zeroth order energy states and energy eigenvalues, we're going to apply our second perturbation, which is the fine structure. Now, if you recall it, the fine structure Hamiltonian consists of a relativistic term uh, and a spin orbit term, right? So there are two parts to the fine structure Hamiltonian. The relativistic term was diagonal in both the uncoupled and the coupled bases, whereas the spin orbit term was not. If you recall, the spin orbit Hamiltonian went as was kind of, well, might as well just write it out. That spin orbit Hamiltonian was E squared, had all these terms out front, 8 pi epsilon naught m squared c squared times 1 over r cubed L operator dotted with the S operator. And this spin orbit term is not diagonal in the uncoupled basis we're using as our zeroth order states. However, the states that it does couple, the off diagonal terms are non-degenerate. So what we can do is we're going to use non-degenerate perturbation theory to determine what the corrections due to this spin orbit term are. And we end up with those spin orbit corrections to first order are going to be the NLS, ML, MS matrix elements. Right. Carrying this all out and plugging this Hamiltonian in there. If you recall, there's sort of the spatial part of this operator and then the spin part of the operator. So what this is going to equal is, well, the just constant terms we can pull out front. And then the spatial term is that 1 over r cubed matrix element, that integral that we calculated previously, and the spin parts, or the angular momentum parts, are the parts that we're concerned with, is this L dot S and S term. Now, we previously have discussed how L dot S, that as an operator, can be rewritten as 1/2 the raising operator on the orbital angular momentum and times the lowering operator on the spin angular momentum, plus sort of the converse of that, plus LZ SZ. And so we can sub this in as our operator and determine what those elements are. If we look, we can see, this term of the Hamiltonian is diagonal in these bases, and it's just going to give us an m sub L, m sub S, h bar squared term. And this term here, only couples adjacent L and adjacent S states, right? This is going to raise or lower these ML and MS numbers by 1. So all the diagonal elements are 0, right? You're not going to have any elements where in this matrix. So we're looking at the diagonal elements of this operator. They're all 0 for this term in it. So this is the only term that survives this spin part of this energy correction. Putting that all together, we arrive at that first order energy correction thanks to the spin orbit term. It's going to be E squared over 8 pi epsilon naught m squared c squared times that 1 over r cubed times that ml and ms h bar squared term from this lz s sub z part of that operator. This part here, again, we've solved previously. if you go all the way back to equation 8.89 from when we were first talking about the hydrogen atom, we showed that that 1 over r3, r cubed term was essentially just equal to 1 over the Bohr radius cubed, n cubed, L, it's cubed, sorry, L plus 1/2 times L plus 1, right? So knowing that term right there, we can plug this all together and get the energy correction to first order due to the spin orbit term of our Hamiltonian ends up being E squared over 8 pi epsilon naught m squared c squared times that term we just stated, cubed n cubed L plus 1/2 times L plus 1, and all this times that ms ml h bar squared term. This all simplifies if we plug it in and convert it to that alpha that we've been using. 1/2 the fine structure constant to the 4th mc squared times ml ms all over n cubed L plus 1/2 L plus 1. And that's our first order correction due to the spin orbit term. In the when we do it in the high field limit. If we add to that the relativistic fine structure term, the total fine structure correction to our states ends up being 1/2 alpha to the 4 mc squared over 3 times 4n to the 4th minus L plus 1 minus ml ms all over n cubed L plus 1/2 L plus 1. And this is the energy correction due to the fine structure term in the high field limit. So again, we have, putting this together, we have the correction due to the Zeeman term in the high field limit, and then we perturb that case with the fine structure term, which gives us this correction. Putting them both together, we get the full shift in the high field limit in a high external magnetic field. So we've looked at the high magnetic field and the low magnetic field case. Obviously, the last thing left is sort of the intermediate magnetic field, where the external magnetic field strength is such that the energies associated with the Zeeman shifts are about the same order as those due to the fine structure. So what do? We don't exactly apply one and then the other. We're going to have to treat both the Zeeman term and the fine structure term of our Hamiltonian as one single perturbation Hamiltonian and apply that to our unperturbed hydrogen states. The problem is that there's no good basis to sort of do this in, right? If you recall, the Zeeman term is diagonal in the coupled bases, uncoupled bases, and the fine structure, Hamiltonian is diagonal in the uncoupled bases. So there's no good bases where this perturbation is diagonal. So we don't, we don't really get to choose an ideal basis. So we just pick one, right? If we do that and we take these Hamiltonians and put the full perturbation Hamiltonian in the coupled bases, what that looks like is this. we're looking at sort of the 2p states where we have n equals 2, L equals 1. Those unperturbed hydrogen states, we're looking at that subspace, and we are in the coupled J M sub J subspace or bases where these basis states are the 3/2, the 4 total angular momentum 3/2 states where we are coming down through those Z components, and then the 1/2 angular momentum states. And that's also with A is equal to 1 over 128 alpha to the 4 mc squared. So that's associated with the fine structure term, and B is equal to mu B times B associated with the Zeeman term in this Hamiltonian. Now, if you recall, when we looked at the low field limit, we were taking this Hamiltonian. So in this coupled bases, all the terms with this A are along the diagonal, and that's because the fine structure term is fine structure Hamiltonian is diagonal in this coupled bases. The Zeeman terms are not diagonal. They have diagonal elements, but they also have these off diagonal elements. When we were looking at the low field case, we were applying degenerate perturbation theory to these two separate uh, subspaces. And since these off-diagonal terms couple separate degenerate subspaces, we were able to ignore them and just diagonalize the appropriate degenerate subspace. Since this perturbation, this Hamiltonian, is being applied to the unperturbed states, where they are every state listed here in this basis is degenerate, we're not able to do that. So we have to go through the full degenerate perturbation theory and diagonalize this full matrix, which is, well, let's be honest, it's a it's a 6x6 matrix. It can be a bit tedious, but it is doable. I'm not going to do it here, but it's done in the textbook, and well, not the details, but the result is given in the textbook, and it looks like this, where we have the energies associated with our 2p states and how they split as a function of external magnetic field. Uh, and the strong field limit we derive separately, and the weak field limit we derive separately. This process, where we include both perturbations at once, kind of brings those two together and covers the intermediate field as well. Now, we've been looking at the 2p states. We can also revisit the 1s states that we looked at a while ago when we were looking at the hyperfine structure in the hydrogen atom. If we're looking at the 1s states, the fine structure and the Lamb shift, neither of those remove any degeneracies. So if we were to apply the Zeeman effect and consider that perturbation to the 1s states, we would have to treat the hyperfine sort of the same way we treat the fine structure term here, because the hyperfine perturbation and the Zeeman perturbation are both diagonal in different bases, and we could do the same sort of thing where we would split it into 3 regimes depending on the field strength for the Zeeman term: a weak field, a strong field, or an intermediate field. And we can consider that the same sort of thing. How does that external field perturb our 1s states? The textbook goes through the intermediate field case. I'll likely have you do the strong and or weak field as homework. But again, we're doing the same sort of thing. Essentially, what we've done for the last few videos is take our hydrogen atom solutions and consider different perturbations and how they can change those hydrogen atom energy eigenstates, those NLM states, and how different things like the fine structure and external fields will shift those energy levels. If we're going to discuss this a lot more in our synchronous sessions and hopefully get comfortable with it with a few homework examples. If you have any questions, please reach out to me, and I will see you in the synchronous sessions.